laboratory includes undergraduate and graduate courses in machine learning, artificial intelligence, data mining, natural language processing, data science, and big data. Dr. Sehra is renowned for his analytical prose. Dr. Sehra specializes in indoor-outdoor navigations and intelligent transportation systems. He has supervised 19 master theses and authored more than 80 peer-reviewed articles published in leading academic journals and conferences. Beyond his academic and research endeavors, Dr. Sehra is an editorial member of several prestigious journals and serves as an academic reviewer for numerous journals and conferences within his domain. Dr. Sehra is also a co-founder and director of Sabudh Foundation in India, a data science organization dedicated to social initiatives. So, through Sabudh, he is instrumental in developing an incubation center for artificial intelligence and machine learning aimed at empowering the youth of India. His commitment extends of using the technology to address the social issues effectively. So I welcome Dr. Sehra for the expert talk.
Thank you, Dr. Pankaj. It's been a great privilege to be part of this program. Thank you so much for considering me and the administration, as well as all the organizer who are making, this program a success. Um, so, can I start with my presentation, or am I audible clear?
Yes, sir, you are audible, and thanks for
Okay,
sparing the time because I
great.
know that there is a time difference of Indian Standard Time and you are sitting there in Canada.
Yeah.
So instead of
No, no, that's
the
okay.
time difference, you have spared the time. We are grateful for that. Sir, you can start the session. You are completely
Okay, great.
audible.
Great. Thank you so much. Yeah. If there will be any lag in the audio because the session is online, please let me know and I'll try to pause my video and we go forward from there. Okay, good evening, everyone. So as Dr. Pankaj has briefed about me, Um, my focus of research is into indoor-outdoor navigation systems. Um, and from last year, I'm focusing more on large language models, how those can be used for intelligent transportation system, language navigation, deliver autonomous vehicles. That's where we are building our technology right now. And I'm very much interested to collaborate with the researchers from various domains to into the area because autonomous vehicles is definitely something which is going to be reality, whether every aspect of our life. So large language models and a combination of autonomous vehicles or robotics is going to be the reality very soon. It's already a reality, and we are trying to collaborate on those aspects. Today's topic is interesting. Let me share my screen. I hope my screen is visible to everyone. Please thumbs up if
Yes, sir.
it is
Yes, sir, it is
visible.
visible.
Yes, sir,
Yes,
it's
sir.
Great.
visible.
Yeah, great. So today's topic is interesting because we are going to talk about ensemble learning, which is a combination of multiple um, machine learning algorithms and how different algorithms work together to make a success. So the topic of interest here is cybersecurity and its defense. Cybersecurity, you have been into this session for 2, 3 days, and I hope that all the context has been set up and your interest is already into cybersecurity, so you know the fundamentals of it. And now we are trying to find out how machine learning can actually assist us in dealing with some of the scenarios that we have in cybersecurity. Now, when we talk about algorithms, every algorithm is having certain bias toward a given type of problems and given type of data set. Now, when it is biased, so it means it has limitations. We have known things like algorithms based on the complexity, based on time, space. So that particular issue is always carrying forward with the algorithms, and no algorithm is perfect for every situation. So that's where it actually creates a new domain to combine different algorithms together because each one has a unique visibility, has a unique capability to look at what is the aspect of the data that we wanted to look at. Now, cybersecurity, just like medical, is very, very typical. We want our algorithms to be very strong to identify, the outliers also. So those are kind of the things that we will be discussing today. I will be discussing few ensemble methods. We'll try to understand what those methods are, what are different aspects. Then we will also talk briefly about autonomous navigation, how and what are the problems that are there. Federated learning and connected and autonomous vehicles, that is one slide dedicated to it. I know you have a next session by my friend Dr. Sandeep Singla. He is going to talk about this topic, so I won't be detailing too much about the technology, but there are certain issues that could be, highlighted. And then the large language model, which is more futuristic. People are there is mushrooming on using large language models into every aspect of our life. Like us, we are also trying to explore large language models into ITS, and we are developing the technology. Then we conclude the today's session. So there are certain challenges that are there. All of you are aware of that in cybersecurity, we wanted to detect um, outliers particularly, and there are threats, and some threats are really, really bad, and we have zero-day attacks, we have advanced persistent threats. So those are always looming, and we need methodologies which can let us know when something is going to happen. Kind of, it is a hidden pattern that we wanted to identify. All these attacks are actually the attacks that give a persistent time to the user to the attacker, and they are trying and having a loophole in the system that is allowing them to exploit the system which is running there. Now, traditional methods were capable of uh, identifying certain type of attacks, but as the technology is becoming more sophisticated, the attackers are also becoming more sophisticated, and they're trying to actually target the loophole. So there is a well-defined branch to find out these loopholes, and then there is a branch that is trying to identify if somebody attacks. Now, how we can look at machine learning can be used to identify that. That's the topic of interest today. Uh, Machine learning models, they have their inherent problems. So one is overfitting. We will talk shortly about it and bias and poor generalization. So, because of these two, three properties, there are issues which are false negative, means if there is an attack, it is not identified. There are false positives, like even now we misclassify legitimate traffic. So, we would like to um enhance uh, basically, we want that our model should be able to identify the attacks, and there should be less false positives. So we want it to be more true positives in our model. Now, because of these problems, there are always issues that our models can miss. So in on that line, we wanted to enhance that capability. So traditional and single model approaches, they basically, as we have discussed, that every algorithm has certain bias. They have some strengths, they have some weaknesses, and because of that, there are false negatives which are more problematic for us. So false negative is very bad because we are not able to identify the attack. So we wanted to enhance the detection accuracy and reduces the false positives. And we want uh, that the combination of the models should be able to do that. Now, when we integrate diverse models, it enhances and increases the robustness of IDS, which further requires discussion or research on interpretability, efficiency, and scalability. So these are very generic things that happens to when we amalgamate different models together. Those models create a very complex structure. Now, we do have explainable AI, we do have some other algorithm which can tell us how and which of the parameters is most important for us. But again, it depends upon the type of the problem that we are solving, the type of the data we are dealing with. Some of the very well-known problems which are dealt, and there is research into this area where ensemble methods are already used, is intrusion detection system, where a random forest have been used a lot for identifying malicious traffic. We have boosted models that are used for anomaly detection. Then we have malware detection and network traffic analysis. So these are some of the problems which have varying or different type of data set. One is data set at rest, and for another one is the data which is live data. So in that scenario, we have to have different type of algorithms that will help us to uh, find out the attack. Now, particularly, I will be focusing most of my lecture today at ensemble learning, what it is, and how we can um, amalgamate different algorithms. Some algorithms are designed in a way they have that capability. And if there are algorithms that they don't have that capability of amalgamation within their self, we can add them together. And there are some standard practices, so standard methodologies there for doing ensemble learning. Um, so combining multiple machine learning models to improve prediction accuracy and robustness is what it is called an ensemble learning. And in this again the same thing, like each algorithm will have certain bias toward a data set, or it has some strengths for a particular problem domain and some weaknesses for another domain. Now, when we wanted to have use it for a problem like identifying attacks, we definitely want it to be a little more robust. For doing that, we will be collaborating and amalgamating different models together. So if different model makes different mistakes, we can simply average the prediction. That's the easiest way. Like if you want, that there should be a task that must be completed. We ask three different people to actually do it, and whatever is the result, we average that out so that the error is small. Why do we need those accuracies, and why do we need those confidence? As a data scientist or as a researcher, you always want to have a quantitative verification of the results. So for that, you need the confidence level on saying that, okay, the model that you are using and presenting is robust, is having a confidence of certain intervals. So all those results must be statistically measures and validated. So there are the first type of ensemble learning is voting classifier. So if we are classifying, what we do is we have multiple algorithms and each will have its own prediction. So one class or one label. And in voting classifier, there are different approaches. One is called hard vote and other is called soft vote. Now in hard vote, the majority of the class wins. Now, normally, when we talk about voting classifier, we always have odd number of algorithms. Those are working in on solving the problem, so that there is always a possibility of win-win. That there should be majority of algorithms are deviated toward one particular result. Now, when it is soft vote, we basically add the class probabilities over the model. Now, each model will be giving us some probability. I consider that you have, machine learning, and that they generate probabilities, and then the probabilities are actually converted into the labels that we wanted. Now, this happens throughout all the machine learning algorithms. When we talk about classification, if it is regression, definitely it is going to give us some quantitative result of the data. Um, and further, we can also weight the different results from different classes. By default, all classes are considered equal. So, based on these two approaches, for the soft vote, if the probability of a particular class over different algorithms is higher, then it makes it to tend to a particular class. So that's how it's a regular additive property that is being used to identify. So in this particular um, example, we have three different models that and they are basically trying to work on identifying, and solve the problem. Now, what I have shown here is a logistic regression. Logistic regression is trying to identify the boundaries. Now, these are the boundaries that are learned over the time to differentiate the different classes. So it has gone wider. Particularly about the decision tree, we see that it is kind of a rectangular shape. And why it is rectangular shape is because of it's a tree. So the decision boundaries are going to be rectangular all the time. But we can club them together based on what is either it is hard vote or the soft vote. So definitely we need other algorithms to be participating into it, or one certain class of algorithm with a different parameters that could be used. So how we will choose different algorithms to be amalgamated, that is also a mastery that we need to do. Uh, the most important aspect of algorithms is bias and variance. Now, what is bias and what is variance? This is a property that impacts the model. So, if we talk about regression models, now in regression model, what we wanted to find out for a given x zero, so given value of particular predictor, we would like to identify what is y. So how we find out what is the quality of the algorithm is by identifying expected value, which is the square of, so I write it like this. Now, this is actually made up of three things. One is variance, which is variance of value, plus we write it down here, bias. And the third term is variance, which is of epsilon. Now, this is irreducible error that is there. Now, these two terms are very important. So whenever you see in the next slides, so there are two items that are mentioned. One is variance and one is bias. Now, let's go to discuss what is variance and what is bias. Now, when we build a particular model, we do not build it onto a single data. We train it for multiple batches of the data. And when we train it on multiple batches of data, we try to create a robustness to the model. Now, variance is amount of by which this prediction would change if the estimated it using a different training data set. Now, different training set will result in different value of prediction, but ideally the estimate of f should not be varying too much between training samples. Let's suppose we have training sample T1 and prediction is Y1, and if it is T2, then it should be somewhere around Y1 plus minus some delta value. It shouldn't be too high. So this should be small actually. That's what is an expectation. So when we have one model and then another model, or when we have one model and we have given different data set, then the outcome should not be changed too much. That's called a variance. And the bias is actually is a fitment to the problem. Now, if we are considering a real linear regression model, so just like if this is the blue dots are the samples and are this line is actually a regression line. Now we can see the bias is actually the difference between what we have predicted and what is actually given here. It is a fitment to the data. So how far our model is from the actual sample that give us the bias. So error introduced by approximating a real life problem. So the real life problem is actually non-linear, but we are trying to keep it simple. We trying to put it like a linear line, And because of linear line, there is a difference. There is an error term that's called bias. And if we have linear models, then definitely that will be, even if we are changing over different samples, it is going to be almost similar. So these two are the key players in identification of what is a better method. Although there are some metrics that are used for identification whether a model is good or not, but for ensemble methods, ensemble learning, these two are the key players. Now, what this example is saying, we have degree one. Degree one means that the model that we are trying to fit is linear. So this is our model that we are trying to fit to this data. And this orange line is a true function. That is the most closest we can go. As we enhances the degree means we are trying to add more features into the model. The there is a flexibility in the curve. Now that flexibility will be actually making our model to fit more towards data, and then the error terms or residuals will be very, very small. Now we can see that at degree 15. So what is the meaning of degree? Let's suppose our initial model was this one, and then we are trying to make and add the power 4 of this, which is non-linear term. So we are trying to make our model non-linear by adding polynomial terms. And at degree 15, our model is exactly following the data which is there. You can see that our model is actually trying to reconnect every dot that is available. So even though there are some small missings, but we have added enough of flexibility into the model that it can capture the information. Now, for a model, we use R squared error. R squared error is basically um, saying that how much our model is able to represent the actual Y to make prediction. So in this, when we have a very nonlinear model, the bias is very, very small, but the variance will be high now. Why variance will be high? If let us suppose I have this model and now I change the data set to some other data. So let's suppose the data is like this. Now in that scenario, the model that we have fit will be following the shape but will not be actually passing through, and then the error terms will be much, much higher in comparison to what we have generated here. So bias is going to be high. So these two are the key players in identification of what models should be actually added. I hope I'm on onto the track. If there is any question, please let me know. Any thumbs up or message will be good to actually let me know, because I'm not able to track um, the chat. So there are three key strategies that allow us to actually ensemble different models. Now, one of them is called bagging. Now, bagging, it involves training multiple models on different input subset sample and then averaging out their prediction. So they're very straightforward method. We give multiple models. They train on to input samples. We can create different samples. We can create onto the same sample, and then we average out their prediction. Now, why this is important is because every algorithm has a unique capability to look at a different aspect of the data. Now, some are really good at outliers based on their boundary conditions. Some are really good at identifying the patterns that are hidden there. Some are really good at, identifying and have nonlinear structure. So they have very optimal bias. Now, one thing that I haven't talked about is bias variance curve. That is very, very important for this whole thing. Now, usually the bias, as the flexibility of the model increases. So what is flexibility? I hope that everyone knows here. Flexibility is a number of terms those are added, the non-linearity that has been added. So more the number of features those are added, more the flexibility is, more a lesson will be the bias. And bias will reduce, but variance will increase. So this is variance. So as flexibility increases, the bias will decrease and variance will increase. And now this is the optimal point that we always want to find out. And that's where we have to actually work through different tries. That's why no model is actually perfect in every situation because it is more data dependent. Now we look at this very point to identify what is bias and what is variance, and they are not directly proportional. So if bias decreases, variance starts to increase. We would love to find out this U-shaped structure where both are lowest. So our objective for identifying a model is to identify where we have bias and variance is controlled. Now, what is the meaning again? The flexibility. We can make our model as flexible as we want, but it won't be helpful. Now, there are two things why it won't be helpful. One is because if we keep on adding flexibility, the model, if flexibility means keep on adding features, the model will start to give you higher error for unknown data. The other one is called explanation. That is also very important, particularly when we talk about our traditional model. Explainability. Now, if you see, mathematicians particularly, they always love to have a model that can be explained. Let us suppose you are a data scientist or working on a problem where you are trying to predict sales. Now, if it is sales, we would like to have models where we can define, okay, what predictor X1, X2, X3, which of these? Like this is spending on news, on this is spending on radio, this is spending on news articles or newspapers. Which of these different predictors is actually helping us to increase the sale by manifold? So we want to have a very interpretable model. And if we keep on increasing the flexibility, the interpretation will go away. And that's the problem with deep learning models. Like we don't know what is the intrinsic model, which and we cannot explain, and that's where XAI comes into picture. So there are packages that are used to identify the importance of the features, which feature is most important for our algorithm. Coming back to bagging, this is one of the approach that is used um, to have average out the prediction. The boosting is another approach. Boosting, uh, in this, it is multi-stage machine learning approach where one machine learning learns the mistake of its predecessor. So you could think it of as in a pipeline where we have machine learning model one, machine learning model two, machine learning model three. And these models are working cohesively. They wanted to solve a particular problem. So whatever mistake this will do, this ML2 will try to learn that and create a stronger, model. Now, when we talk about modeling, what it is actually doing is creating decision boundaries, and that's where, which is very, very important for us to understand what is the decision boundary of a model and how the decision boundaries of different models can be connected together to create an ensemble model. Now, it results in a very strong learner capability, making improved prediction, reduces bias in the training set. So again, we will see these terms coming up because this is where we are focusing on how we can, come up with an algorithm that has lowest bias and has lowest variance. We wanted to control those parameters. The third approach, which is very innovative, that combines the models. Now, rather than having just set of models connected to each other, this is actually a two-level ensemble learning technique. What does it mean? Like we have multiple base models, and those base models create further prediction, and that further prediction is used to train another model to find out what is the best decision boundary that could be created by amalgamation of these models. Maybe when we go to discuss on a particular algorithm, then it'll be more clear. So what is advantage? Reduce overfitting and improves generalization, enhances robustness and adaptability. So these two terms are correlated. If we have higher bias, uh, we say underfitted model. This might be a little more, you might be more knowing it, underfitted, and otherwise, if it is having a higher variance, that is called overfitted model. I hope I'm clear till here. Any thumbs up or any questions, you can stop me by. All good? Okay. So different models work at different part of the data. Individual mistakes can be averaged out. Um, and this is important. So which model should be combined? How do we identify what to combine and what to be used as an ensemble model is based on bias variance analysis. Now, if the model or the total model that we are using underfits, means high bias, low variance. It's more like very inflexible model or a straight line for now you can consider, which has high bias but low variance. It's not changing as the data is changing, so the error terms are going to be around the same. Then we can combine this model, the high bias model, with the low variance with other low variance models, and this will further reduce the bias. So because we have different I think there was some issue with the internet. Let me share my screen. I'm audible, sir? I'm
Yes,
audible?
sir. Yes, sir. Audible.
Okay. Yeah, there was some issue. I don't know. Um,
No issue, sir. No problem.
yeah. If the model overfits, we have low bias and high variance. We can combine other low bias models, and that can be done by bagging. So boosting will help us if our model underfits. Bagging will help us if our model overfits. And one thing that needs to be that's a good point to actually consider when you're talking about and when you want to work on ensemble model is models must be uncorrelated. So if the models are trying to look at the same type of thing, then we should actually not consider that. So that is also another valid point to look at. We'll learn about how the stacking is done in the later part of this particular presentation. So I'll quickly go over some of the model that has in already built-in capability of this. But before we I'm going to discuss it, I would like to brief about decision trees because trees have are very strong category of machine learning models, and we will enhance their capabilities here. The trees split the data points to the leaves based on the test. Now, what is the test here? It's based on certain parameter with we set up some threshold, and once we have the threshold, we would like to know what is the split point. Now, evaluation is done based on loss function, and we have impurity, Gini index, or information gain. Those are what we look at, which of the feature needs to be used here. Um, Optimization usually is greedy and recursive. We try to look at each and every parameter or feature that should be that is there in the available data set, and we try to find out the most important parameter that could be used to create a split point. Now, when we create a split point, we are actually creating these decision boundaries. So that's where this decision boundaries start to appear, and then we further divide it, and these smaller decision um, uh, boundaries are created. Now, based on the leaves, the purity of the leaf nodes, what class they are in, we would have these red labels or blue labels, and based on that, the class will be dedicated to it. Now, so how do we calculate the split point is done by identifying the information gain. So that is what it is. It's a mathematically calculated values that will enable us to identify which of the parameter have highest importance in the data. Now that is the data which has capability on making decision onto the response variable that has more power to drive the data, and based on that the response variable is actually acting upon. Now we have entropy, we have information gain. The split will be based on a feature with highest information gain. Now, regression as well as classification trees are can be created. When it is classification, we will talk about the class. And when it is a regression tree, we will be talking about the mean. So what does mean? Mean is the number of uh, items in the leaf node. So let's suppose this is x0, x1, x5, and x7 is there. So based on that, whatever their value of y is, we will try to take that as a predicted value for this node here. We choose a split that minimizes the squared error of for the leaf. So this is our loss function that we are trying to predict on. It will yield, although it is non-smooth, stepwise boundary. So the decision boundary you could see is actually being created by blue or by this green dotted line. And we have split our data set into two parts. One is training and other is the test. So very basic approach here. Um, in the decision trees, we have most significant features and they impact the result a lot. So all the time, this will be the one, the worst radius is going to be the one that will be selected because of the importance, because of its information gain. This feature will be selected, and that is a bit of problem. It does not allow other features to contribute much in the model, so maybe this creates a situation where we need to think of, we need other models also. Now, one particular feature should not be driving all the models. It is good that, okay, one model is good dedicated to this, and then we have other models too. And this sort of things actually create situation where we need to think of that ensemble modeling can be a better way to actually judge. Now, shallow trees are basically have high bias and very low variance. Deep trees has high variance and a low bias. Now, when it is deep trees we have to keep bias low and reduce the variance by using bagging approach. Now, this is where you get to know about what you need to do with the model. So if the bias is low, you want to keep it low, you want to reduce the variance then, and you have high depth trees that are being used because you want to enhance your capabilities, then use bagging approach. And if you have shallow trees, you want to keep the variance low and reduce the bias, you have boosting as an approach that could be utilized. Now, this is a curve that I was talking about. Although we will have seldom situations where the bias and variance will have a perfect U-shape situation. So normally you would say see something like this, and we need to have keep on increasing the depth actually to actually see the point like a U shape is coming, but it gives us some point that where the intersection, that's where we have to actually identify what is the best depth. Now for this, sometime we do cross validation, which is a great approach to actually find out and optimize the parameters to do hyperparameter tuning. I hope that you have already done that, and that is an approach that will be used a lot to actually control and identify what is the best value for this. Um, so bagging reduces overfitting by averaging out the individual predictions. More bootstrap sample. Bootstrapping is an approach which creates unique samples from the same data set. And that is usually used to create and train the model. So when we do not have lot of data, but we want our model to see data sets. So we can use bootstrapping approach. Higher the number of samples, more models there, more smoothing will be there, but the training will be slower. Base model should be unstable and different training samples yield different models. So very deep decision trees are could be one of the outcome here. The deep neural network can also benefit from bagging approach, which we have giving different data set to different models and then taking out their prediction. So either we can use soft voting for classification, or we can do hard voting, or we can have, if it is for regression, we can do a mean value for the final calculations. Now, random forest algorithm, those are most capable models which are there. Um, and we have seen that they are really, really good for most of the problems that we do now when we talk about traditional models. And my thought is, for particularly for machine learning, we do not need to go to utilize complex model if the simpler models are good enough. The simple is always better. It has more control. It has more, approach to do it. Deep learning is not always a required algorithm. Random forest algorithm is always kind of a top-notch algorithm. SVM, random forest, these two algorithms are used in so many applications there because of their capabilities. We will talk about forest, a random forest, because we started with that discussion. So random forest has its inbuilt capability where it tries to create multiple trees, and each tree is created based on different set of the features. Now we have to work on that, but definitely there are some um, parameters that could be passed to the algorithms to actually identify how we want to create split and how many features we want to discuss on. If we want to create extremely randomized trees, we can consider one random threshold from random set of features, and which is going to be faster. No calculations are done. So what we are seeing here is multiple trees are actually created in random forestry. So hundreds of trees will be created. Each tree will have its own boundary. When it is a different boundaries, so let's suppose we are talking about here 4 or 5 models, and we can club them to create this decision boundary. Now, the crux of ensemble model is actually creating a decision boundary that has more visibility and capability to distinguish the data, and it is more, more powerful. Now, increasing the number of models means trees here decreases the variance, so less overfitting. Bias is mostly unaffected, but will increase if the forests become too large. Too many, uh, uh, trees we are creating. Again, cross validation help us to identify what should be the optimal, but normally if we see, based on uh, my knowledge, what we have seen, something in the range of 200 to 500 a number of trees is always going to be a good try to look at how model behaves. Now again, we are looking at variance, bias, and error. This is epsilon, which is also reducing as the bias is almost, very much stable here, but variance is decreasing. So it means that the models are becoming more robust as we keep on increasing the number of trees that we wanted to generate. Now, by this is already having that capability built in, which is required for ensemble models. Now there are different class of packages which are there. So N estimator, max features, these are some of the hyperparameters that you do for your research to actually identify what is the best value of these parameters will enhance your algorithm and its prediction and robustness. Now, for random forest, we do not need cross validation. Why? Because we can use one error out of bag error. What it is basically very similar to cross validation in each tree grown. So again, random forest has built-in capability of doing that cross validation. It always tries to take out 33% of the samples out of bag when it is training. So other part is used for training, and this is part that is kept out of the bag. So for each tree that is being created automatically by default, it is doing, and we can look at this particular feature to identify what is the best value. So we can see how our error changes as we keep on increasing the estimator. So we can use this particular parameter to optimize and identify what is the best the way of what is the best model that could be created. Now, random forest, square root, log 2, and none. So when all features are being utilized for the model. Now, this picture is showing us how many parameters are important. So in comparison to decision tree, we can see that there are a number of other features who are also playing very important role. So it means that the model has started to look at other features which are there in the modeling. And when there are other features, they are given value, we would have more chance to actually identify those anomalies which could happen in the data set. So there will be some models that will be highlighting a particular thing into our data set. Now, there are certain problems again. Um, we are trying to discuss some solutions and some problems with the models. Model calibration is very, very important. Now, what is model calibration? We know that models do create probabilities, and those probabilities are not truer form of the probability. It doesn't mean that if I say my model generate 80%, it means that 80% likelihood of that particular thing. So model calibration is required in random forest. They are poorly correlated. Because they tend to overfit their probability. So they want to push the probability. If they think that, okay, a particular observation is into a particular class, they tend to overfit that probability. So it's a not true representative of the actual probability. We need to calibrate it, and one of the method is isotonic regression, which is non-parametric, or we can use logistic regression also to actually create a actual probability of the data set that is here. Now, warm starting is another approach that gives ensemble trained for iterations. You can simply add more models, and this is actually called warm start, where we have existing model, and instead of restarting from scratch, we can keep on adding different models to the existing models. Now there are certain problems again where that is not ideal if the data batch changes over time. What would be concept drift is that our previous model, so let us suppose M1, whatever it is, so conclusion or made from bagging approach of multiple models, this will not be able to see the neo data because neo data is added to this model only. So there is a concept drift. Um, Boosting, if we see, is better on this approach where we don't require too much of calibration and warm starting. There are strengths, there are downsizes of each and every approach. Now, the next one is called adaptive boosting. So, this is a boosting approach where we keep on building based on the previous model. So adaptive boosting or XG boost, or there are some other recent models that are very much capable of. So what we are trying to do is we obtain different models by reweighting their training data every iteration. So we reduce the underfitting by focusing on hard training examples. If there are some there are some certain instances that cannot be judged very well. The weight will be increased for those particular instances. So increases weight for instances which are misclassified by ensemble. The base models are basically simple, and different instances of different weights lead to different models. So for for this particular approach, we keep on building further based on the models and then keep changes the weight of the instances. Now, additive, it is an additive model. Predictions at iteration I are some of the base model predictions. And in EDA boost, each model gets a unique weight. So we have set of models, and each model will have a unique weight that is given. uh, Now, all this is learned based on this loss function, which is here. So we will try to minimize this loss function, and based on the epsilon. So epsilon, we know there's a residuals, and based on the residuals, we get to know about what should be the weight that is given to that particular model. So based on that, we adjust the weight of different models, and that help us to actually find out the final model. Now, in EDA Boost, we can see that we have weights are adjusted. So this is base 1. Further, base model 5, base model 37, and base model 59. So we can see that the decision boundaries are being created and improved over time to actually create the final decision boundary. Now, here we have another example. So we have input data, which is one tree. We can see that the decision boundary is linear and dividing the data approximately half. And then we have three different trees, and then we have 100 different trees. All these are showing us how the decision boundaries are created. At AdaBoost 100 trees, we are able to classify very, very accurately what the data looks like and what are the decision boundaries for the data. Although there will be some misclassifications that are there, but this is a great improvement over a single tree which is being utilized. Boosting is bias reduction technique, and boosting too much will eventually increase the variance. So we have to think of when and how many number of trees that could boost each other. Again, that becomes a hyperparameter for the calculation, but it is generally a bias reduction technique. If you see that your models created on the data set, you're not able to fit the right model onto the data, then definitely, and you have high bias, then look at this boosting approach to reduce that bias. Um, Gradient boosting, which is used a lot. You might have heard of XG boost, which is the advancement of this. So what it does basically, in each iteration, the task is to predict residual error. Now, what is epsilon? What is the difference that is there? Now, in this model, we try to find out the pseudo residuals that are computed according to differential loss. So loss function is there. And based on the loss function, we know that for if it is regression, the loss function is the least square loss and log loss for classification. Now we try to identify this pseudo residual, and wherever this creates minimum, we try to fit the model onto the residual. So that's something which is done for gradient boosting. So one model will create a residual. The next model will be trying to make prediction based on those ready residuals. So that is how it is done. I see that there is some issue with the visibility of these, but I don't know why it is coming. These formulas or yeah, so these formulas are used to identify the loss function, and based on loss function we identify the residuals, and once we have that residuals we fit new regression tree model to Ri. So pseudo residuals are used to fit the next model. So that's how we will be able to quickly reach to have a better decision boundary. So we can see that in the previous approach where we were talking about trees, uh, in comparison to that, where we have hundreds of trees, we can see that within certain steps of 10 steps, our residuals are quickly dropping to zero. So almost our model is capable of finding out what is the data. So in first prediction, we find the residuals. This is a residue, this is the residue, and this is residue in the 10th approach. Now, in every next build that is done, it is done based on the residual. So that is how boosting keeps on moving and keeps on increasing and correcting its decision boundary. So this is an example of that. So this is our first model that created this rectangular boundary. This is our fifth model that has learned from here to here. This further taught teaches this, and this further teaches this, and now that's our base 59th decision boundary that is there. Again, there are some misclassifications. We can use them to identify outliers also, but if we wanted to just focus for now onto misclassification, definitely the model is having more flexible boundary and is able to adapt into the data much more perfectly. So this is another example of gradient boost. And we can see that the decision boundary has become much more complex with the 100 trees in comparison to what we have seen for the previous approaches. Um, Here, this is effective to reduce bias error. Boosting too much will increase variance. That's a standard practice. So we can see that all items keep on decreasing, but there will be some point that we have to consider how many trees we would like to consider and how many should be actually utilized. Now here again, it has identified not only one, but there are most prominent, those have been selected by this particular model. Um, Compared to random forest, trees are smaller and hence more features have zero importance. So there are features which have zero importance because the number of trees are smaller. But we identified, we know that there are other parameters which are capable of, have power to identify the stuff. Now, there are similarly, we have another set of hyperparameters that could be utilized to actually identify the the issues. Extreme gradient boost, XG boost, that is used a lot, which is very faster version of boosting. Um, and here it is not, normal regression. We were splitting and minimize the squared loss of the leaf prediction, but XG boost just fit on the residual error. So it's not trying to minimize the loss. It is just going over fitting into the residuals. That makes it much faster, and it has more capability on, converting converging to the data set much more quickly, and has a strong regularization by pruning trees. So we have not discussed about L2 and L1 regularization that help us about tree pruning. There are a few things that we have not discussed, which is part of other machine learning thing. But definitely what we wanted to emphasize here is we have more control on now identifying which of the model is good based on two parameters. One is variance and bias, and that help us to actually combine different models together. Cat boost is a newer technique um, that is much more capable, does not require one hot encoding like other models where we have to prepare our data set for one hot encoding. It works for categorical variables. So it knows how to split the categorical variables, how to do it. So the capability is inbuilt into the model, and it is boosting algorithm. So it learns from the previous algorithm and enhances the model. So it's basically an ensemble approach that is being used, and it allows GPU acceleration. So it has capability to work on GPU, and that therefore is much more capable on working with the large data set. And one of another powerful feature of this algorithm is that it can handle missing data without requiring explicit imputation. And we know that when we are talking about data, lot of pre-processing effort goes into it. More or less, I think around 50% of effort goes on preparing the data. So what value should be used, what imputation technique should be used takes a lot of effort there. But this algorithm has inbuilt capability already. Now let's talk about the third type of approach, which is stacking. Stacking, we have, let's suppose, m different base model that generates a prediction. From the prediction, we will create new features. Now, let us suppose there is x0, x1, x2, x3. So these are some observation. And each model, let's suppose there are three models. So y1, y2, y3 will be created by model 1, model 2, and model 3. So each model will create their prediction. So this is the test data. Now what this will become a new matrix. So this is a new matrix for us. So each model will create this. And now we will use this metric to further create another machine learning model that will help us to identify which of these models are actually more capable on identification of the boundary, or we will use these outcomes to actually create a better decision boundary, which is amalgamation of different models altogether. So three different models, they will be combined to create a meta model, which will be used which will be used by based on the predictions from the base model. That's what it is called as a stacking here. We can use linear models as a stacker. So we have X input, we have base models, and each will be giving us prediction based on the data, test data. and we have a stacker. Now, this stacker is again another model. It could be linear model, it could be a gradient boosting algorithm or any algorithm. That's what will generate the final outcome. Now, so we can see that the computational requirement has increased, but it is at cost of better judgment to our data set. So cascading allows us to add base models, and then extra features could also be added. It is very accurate, but slow to predict. Now it depends whether you want batch processing or you want online processing, and based on that, your results could be taken care. There are many other approaches. Definitely, there's no end to algorithm, and that's where we researchers do experiment with different ensemble approaches to find out what is the best way out for a particular problem. So, uh, this is a snapshot of all algorithms which are there. Most of the problems that are there currently to intrusion detection. They use the base data set. The one is KDD99, and then there is a newer data set which is there. It has a class feature, response variable, which includes a different type of attacks. Those are there, so normal, and then there are certain attacks. So it is a multi-class classification approach that could be utilized. Now, there is a case study that I've taken. They actually used different models and do the comparison for identification or differentiating whether for a given parameter, whether it is an attack or not an attack, and what category of attack it is. So the paper has actually compared different approaches. So bagging, boosting, and stacking. So why stacking? Because we see that predictions are actually amalgamated and then created the final prediction. So bagging is we have different data sets, each is trained, and we got the prediction, and we try to find the best one or by averaging out. The second one is boosting, where we have prediction from one, it is given as input to the next, and so on. So they are more like a sequential set of algorithm, and there we will have the data that resultant is coming out, and the last one is stacking. Now, what they have shown here is individual accuracy. Now, we haven't talked really about these parameters. I consider that all of you know about it, and how we can actually judge about and the capability of the models based on these parameters or ROC curve or true positive rate and false positive rate. That will give you area under the curve, and that's where we can compare different capabilities of the classification model. So based on bagging, boosting, and stacking, we could see that almost they are reaching 100%. The precision is 100%. Then recall is 100%, and this is also very, very similar. So which is most consistent is stacking, because this is most complex, slow, but very, very accurate. So we can see that we are able to achieve a very good result here for the modeling. Okay, just give me a second. Uh, any questions till now? Uh, okay, so let me enhance it. There seems to be some issue with the sharing. Just give me a second. Any questions till now? We can use this time.
Participants, you can drop the query question in the chat
Yeah,
box if you do have.
you can drop it and let me come back. I think there is some issue with the. Okay, so hearing none. So we have. Uh, so what we can see here is. Let me just give me a second, sir. I think there's some issue with the presentation.
No issue, sir. Take your time comfortably.
Yeah, yeah. Um, yeah, so this model has actually tried to. So the model is able to reach a very high frequent the results, and this is our confusion matrix, which says the story. Zero means no attack. One means there is an attack. So true level, predicted level, and the actual label. So we have use for stacking, we have bagging, and then we have the boosting. So all three creates a different um, data, but they are very, very close. We can see the misclassification rate, and the stacking has the lowest misclassification rate. So that's why we will definitely try to look at this particular aspect. Now, the work that we I'm working on is more focused on autonomous vehicles. There are problems that we see because autonomous vehicles are actually continually monitoring and supervising the surrounding environment to detect um, any dire experiences, pedestrians, roadblocks, any traffic jams, and alert the driver. So, and it actually uses the communication channel. So the communication channel is available and open. Now, when it is available, it has also become susceptible to denial of service, man in the middle, which start to communicate with the autonomous vehicle, can hijack it. And one of the problem that we worked on is GNSS snooping. This is also very important because car will also be taking measures based on the GNSS signal, so it can be snooped very very easily, and we somebody can actually navigate and change your mobile location. Like if you are going to one direction, it can show you on to a different route and then try to um, uh, create discomfort for the person who is navigating. um, there are chances of attacks on software and hardware. There are chances that the EV packets those are being sent, they could be intercepted and can be compromised. There are chances that CAN, so which is controller area network used by the car to actually communicate between the electronic devices, that could also be hijacked. Now, one of the study that actually worked on is identifying the compromisation state situation onto the CAN network. So they used a standard data which is available to identify um, the problem, and then they build ensemble classifier based on that. So it's basically there are many others studies out there, but particularly ensemble models, they have shown that the results with ensemble models are much more higher in making prediction whether there is an attack or not. There are some recent methods which are being used. So blockchain is definitely one of the technology that is available. People started to use GAN network to identify the transformer-based models to identify attacks onto the autonomous vehicle, but they are very computationally expensive. Now, with the advances in the hardware, particularly NVIDIA is coming up with so many newer things, and they are launching new products. Like one of them is Jetson, which is very low powered GPU based machine that they are coming up with. So we could utilize and work on these recent models also. The case study that is shown here, they are able to identify that again the stacking is one of the approach that has created a very good results on labeling different classes of the attacks. Now, federated learning is where it is required. I'll not talk much about it, but connected and autonomous vehicle is a reality now. And when they are connected, they have to share data. So, autonomous vehicle usually create 20 terabyte of the data in a day or so. So it's a huge data that is there. Now, if it is connected to the central server to actually plan its routing, plan its motion, plan its the way it is traveling through the traffic. So it's not an independent algorithm that is only fixed onto the car. It is also taking some commands from the central server. When that is done, data sharing is very difficult, and that's where the federated learning comes into picture. Now, because your next session is onto it. So federated learning allows us to only share the model weights rather than actual data so that it actually help us to preserve the privacy and keep the data onto the device and just send the learning parameters to the central server, and that is how it enables us better control onto the devices that are running with the machine learning paradigms. So federated learning is a distributed machine learning approach, but it has its again problems when it is sharing model parameters. They could also be compromised, and somebody else can send the gradients and the weights to the car, and the car can actually start to train the model in a different direction. So in federated learning environment and connected and autonomous vehicles, this problem is very prevalent. Again, there is research going on. Some have suggested different approaches. Blockchain is definitely one of them to safeguard the weights. Then there are different other approaches, homomorphic, differential privacy. Those are there, but it is again we have to go into how we can see ensemble models can be actually used to study different compromised states in this particular state where we have connected autonomous vehicles and we are using federated learning. Last thing to for this particular lecture is about large language model. They are revolutionizing every aspect of it. OpenAI has announced that they are able to um, work on, they are able to realize O3, which is AGI capable model. So definitely things will change in months now. And I think even with the large language model, there are different models that we are trying to see, which are large concept based model or language concept based model, because each model has some problems. The problem with large language model is their embeddings actually, how the embeddings are created. Definitely we can have another session or discussion on this, or we can use a large language model for problem solving. We are trying to train GeoLLMs that are more position enabled, that are more able to consume spatial data as well as temporal data. So how LLMs will work on spatial temporal data and how they are going to make prediction, because LLMs have their own problem of hallucination, and there is an AI that can safeguard, that is called guardrails, that will help LLM to actually keep on to the path. Now, with all these newer set of algorithms, those are coming up, newer set of problems are coming out, and we start to see in the literature that people are talking about ensemble LLM models also. So LLMs can be applied to threat intelligence, vulnerability assessment, network security, privacy preserving, and every aspect of cybersecurity we see. There are certain problems with it. Again, newer model begins new problems, exposing sensitive information because a lot of data needs to go. Again, there will be a problem with the inputs that would be given, just like
Sukhjit
we
sir,
discussed.
Sukhjit sir, I feel
We I'm
regret.
just going to finish it.
I
So
regret
we
to interrupt. Actually, the allocated time is over. So you are having the pool of knowledge. So it's wonderful to learn the things from your side. So
yeah
it is a wonderful session.
yeah,
So
this
we are
is
having
the
the
last slide, so
right,
I'm all good. Thank you so
right,
much
sir, right,
for
right,
this.
sir, right,
Definitely there is lot of discussion that would be done on it.
right, sir,
And there are so many domains that opens up. This is very generic you know, discussion, but certainly specific discussion could also be done.
right, sir.
Thank you so much for all your time. Any questions if you have, you can reach out to me on my email ID sehra@wlu.ca if you want to talk more about it. Thank you.
Right, sir. It was a really wonderful session, and it is my pleasure and privilege to express my heartfelt gratitude to Dr. Sukhjit Singh for delivering such a insightful and engaging talk. So, Dr. Singh's ability to present the complex concepts in an accessible and practical manner have truly left a mark on all of us, and the participants have gained valuable knowledge into how ensemble learning methods can effectively leveraged to fortify the cyber security systems in the era of rapidly evolving threats. So, this session has not only enhanced our understanding of cutting edge techniques, but also inspired us to explore the innovative further in the domain of information security. So I am thankful to the Dr. Sukhjit Singh for the valuable contribution to this adult sponsored FTP on emerging trends in information system security using AI and data science for next gen cyber analytics. So, sir, we are truly honored to have had an opportunity to learn from your experience and expertise. So, thank you so much, sir.
Thank you so much, sir. Thank you so much, and good